Okay, so Amisha, Sanvi, Urvashi, Anisha. So today in this chapter, now we'll study about isomerism. So about isomerism, you people are already aware that what is isomerism. So can anyone write definition of what is isomers? Write in comment box what you mean by isomers. Yes, same molecular formula but different structural formula. Exactly correct, right? So compounds with same molecular formula but different structural formula, they are known as isomers, and the phenomena is known as isomerism. Isomerism actually is of two types: structural isomerism and stereoisomerism. Now about structural isomerism, you already studied in 11th standard, basic principles of organic chemistry. Four different types of structural isomerism are there. Stereoisomerism. Now in this again we have two types. Geometrical isomers, and another one is optical isomerism. About geometrical also, you studied it in hydrocarbon, that is cis trans type of isomerism. And in optical isomerism, now here we are going to study in this chapter about this topic. So structural and geometrical we already have complete, and now we are going to start with optical isomerism here in this haloalkane haloarene chapter. Now what we mean by optical isomerism? So first, to understand this concept of optical isomerism, we need to know certain terminologies. So first we'll learn those terms, what they mean, those terms which we are going to use again and again when we discuss about optical isomerism. First term we have to study, that is chiral center. First term which you have to study, that is chiral center. What is this chiral center? Now this chiral center is actually known by many other names, many other terms, like that is even known as asymmetrical carbon, then chiral center, then stereo center. All these means the same. Now what is this? So actually the chiral center or asymmetric carbon is the sp3 hybridized carbon, which valencies are completed with four different groups. All the four groups attached. As I'm telling you, sp3 hybridized carbon, this is the first requirement for chiral center. After that, when I have sp3 hybridized carbon has four valences, and all the four valences completed with four different groups, and that type of carbon is known as asymmetric or chiral carbon or stereo center. So that is what is chiral carbon. think about shape. What is shape of this carbon compound? So as hybridization sp3, then shape is tetrahedral. So if I have to draw this molecule, suppose this is one group attached, another group attached. So all the four groups which is attached to the carbon, they are different. Shape is tetrahedral. So this type of carbon is known as chiral carbon. Another term which we have to study is PPL. Now what is this PPL? The light source which you use, if this is the bulb, right? How these light rays they spread in all the directions. So if I have to show that, then I use this kind of symbol to show this. So this is polarized light, which has vibrations of light in all the directions. Now to this light, when I pass through some special type of instrument known as Polaroid, then this light get converted into light which has vibrations only in single direction. This light, now vibrations of these rays are in single direction. So this type of light is known as plane polarized light, which has vibrations only in single direction. These vibrations, they are not moving in all the directions as in case of polarized light. So this type of light is known as plane polarized light. Now why we study this plane polarized light over here? So the only aspect of learning plane polarized light is this is the only way we find out that whether my compound, given compound, that is whether haloalkane or haloarene, is optically active or not. So for you finding out that, we make use of this plane polarized light. How? That we'll study further. So these two terms you must know: chiral center or chiral carbon, and another thing is plane polarized light. So this is the arrangement we use to convert polarized light into plane polarized light. This is known as Nicol prism or Polaroid. This is also known as Polaroid. Now for compound being optically active, there are certain requirements. So first thing, carbon should be chiral carbon, or even if you have complex compound, there must be one chiral carbon present to compound being optically active. And second thing, compound be able to rotate plane of PPL. The compound which is there with you, if that compound can rotate plane polarized light, then only that compound is optically active. How to find out this? So here I have my polarized light, my source, which I am passing through Nicol prism. When this pass through Nicol prism, I have plane polarized light which has waves only in single direction, which is known as plane polarized light. Now to this I'll pass through solution of the compound, for which I want to find out whether the compound is optically active or not. So whichever compound I have taken for which I want to find out that whether the given compound is optically active or not. So I'll pass this plane polarized light through this solution of the compound. Now if this compound is able to rotate plane of polarized light either towards, two different possibilities are there. This may rotate plane of polarized light either towards right or towards left. Any direction, but if this compound is able to rotate plane of polarized light, then that is known as optically active compound. So what is optically active compound? Is the compound which can rotate plane of polarized light either towards right or towards left. That is known as optically active compound. So here we discuss what is optically active compound. Now we have two different directions, and based on we have two different class of compounds. Now the compound which rotate plane of polarized light towards the right side, those compounds are known as dextrorotatory. Those compounds are known as dextrorotatory. And another group of compound which rotate plane of polarized light towards left side, they are known as levorotatory compounds. So compounds which can rotate plane of polarized light towards right side, they are known as dextrorotatory. Compounds which can rotate plane of polarized light towards left side, they are known as levorotatory. So first thing, optically active compound. For optically active compound, one requirement, there must be at least one chiral carbon present, and compound which rotate plane of polarized light, plane of PPL, I'll say plane of PPL, is known as optically active compound. Now looking at the structure of the compound, suppose I have one compound in which I have chiral carbon present, and I want to find out that whether the given compound is optically active or not. Is there any way to find out whether compound is optically active or not looking at the structure? No. There is no any way that you can find out that whether the compound is optically active or not only by looking at the structure of compound. Only by this experimental method you can find out whether your compound is optically active or not. This is the experimental method we use to find out whether compound is optically active or not. No any other method we have. Means by looking at the compound you cannot. Now once I decided yes, my compound is optically active, then I have two different possibilities. Either plane PPL rotate to right or to left. If this rotate to right, group of compound is known as dextrorotatory. To this dextrorotatory, even we symbolically represent by plus or D, by plus or D, and those compounds which rotate towards left, they are known as levorotatory. To them will express either using symbol negative or by small l. So this is what is about optical activity. So dextrorotatory, to them we show either using plus symbol or small d, and to levorotatory we show either by minus sign or l. So this way we have two different class of compound, one is dextrorotatory and one is levorotatory. Now One more thing which is very much interesting in these compounds, let I take one example. Here I have one CH3, Cl, hydrogen, and CH2, CH3. If you see, all the four groups attached to this carbon are different. So this carbon is a chiral carbon, and asterisk sign we use to show chiral carbon. Now experimentally we find out that this is optically active compound and this is dextrorotatory. And then if I keep mirror over here, I'll get image of the compound. In image, what I get is CH3 position remains as it is. But when I see from this side, first I'll get CH2, CH3 on this side, then hydrogen over here, and then Cl. This is the arrangement of four groups will get as mirror image. And if this compound is dextrorotatory, its mirror image is always levorotatory. Mirror image of dextrorotatory compound is always levorotatory. Here this carbon, this compound is the same, molecular formula is same, but because their three-dimensional arrangement is different, one is dextrorotatory and another one is levorotatory. So these two are known as optical isomers of each other. These two are known as optical isomers of each other. Now here in this we have 1D and 1L. These two are optical isomers and they are even known as enantiomers. They are even known as enantiomers. Compound A and compound B, they are enantiomers of each other. Compound A and compound B, they are enantiomers of each other. Let I take lactic acid. Lactic acid formula is CH3, then OH, COOH, and one hydrogen. Actually, what is lactic acid? That is 2-hydroxypropanoic acid, which is commonly known as lactic acid. What is lactic acid? 2-hydroxypropanoic acid. Propanoic acid, 1, 2, 3 carbon. On second carbon I have hydroxy group. One more valence is remaining that we have to satisfy by hydrogen. If I draw three-dimensional structure using wedge and dash bond, then here this is present as wedge while hydrogen is present as dash. We have already discussed about these two types of bonds. The wedge bond show that this is coming out of the plane towards observer, and while the dash bond that represent that hydrogen is towards backside of the paper away from the observer. And always keep in mind, broad end we show towards observer. About this in detail we already discussed in 11th. Now again if I keep mirror in between, then mirror image which I'll get is hydroxy group on this side, then hydrogen over here, COOH remains as it is, and CH3. Again, if this is dextrorotatory, this is levorotatory, or vice versa. This we can find out only by experimental method, and that is polarimetry. And that method is known as polarimetry. So that is the only method to find out whether the compound is dextrorotatory or levorotatory, right? So these two are also enantiomers of each other. these two compounds, lactic acid, these two compounds, they are also known as enantiomers of each other. So if I have to define enantiomers, then now see, if I keep my two hands, if this is my hand and if I have mirror in between and this is the mirror image of the hand I will get. So my two hands, they are also enantiomers. Now if I want to superimpose them, they are non-superimposable, right? On opposite side I'm getting my two thumbs. Same way, these two are mirror images. If I want to superimpose the another compound on the first one, then here also these two are non-superimposable. So enantiomers we define as non-superimposable mirror images. Enantiomers are the compound which are non-superimposable mirror images. These are one type of optical isomers. These are one type of optical isomers. One another type of isomerism, under optical isomerism we have to study, that is diastereomers. One, two, three, 4, 5 carbon I have. Here I have CHO, here I have CH2OH, H, OH, H, OH, H, OH. If I draw one mirror image, I will get H, OH, OH, CH2OH, here OH, H, H. So this is my structure 1, this is my structure 2. From this I can clearly say that 1 and 2 they are enantiomers because of same, they are non-superimposable mirror images. Are you all agree with this? I have third compound CHOC. Again, if I keep mirror image, I will get now I have compound 3 and compound 4. Three and 4 they are also enantiomers. Yes. What you can say about 1 and 3? Whether they are isomers or not. Write your answer in the way yes or no in comment box. 1 and 3 they are isomers or not? Even write in structure 1, do we have any chiral carbon present? If I number these carbon atoms as 1, 2, 3, 4 and 5, do we have any chiral carbon in this? And if yes, then which carbon they are chiral carbon? Which are the carbons which they are chiral carbons? Write the number of carbon. Write your answer in comment box. Whether 1 and 3 they are isomers, and in structure 1 which carbon atoms are chiral.